So welcome again. The 10 minutes of breaks are over, a rather short break. And next we have the introduction by Jefferson. Jefferson, are you available? I can't see your background slides yet.
My background slides? No.
Okay.
I was going to start just by talking, but I can also.
Oh, yeah, sorry. Didn't know that. I didn't know that.
It's okay.
Okay, the procedure is the same as basically before. If you have questions, raise your hand or write them into the chat, and I will try my best to sort them and forward them in time to the speaker. And now we have the introduction to by Jefferson. Thanks.
All right. Thank you again, Florian, for that introduction. So this is a short session for a reason. It's supposed to be pretty simple. It's really, you're gonna see how it is. It's really going through some Python notes, some Jupyter notebooks, as you'll see. So recapping once again for those who perhaps weren't here or don't remember, we have the code that perform the simulations, that perform the quantum Monte Carlo simulations, which is ALF, and over the past few months, we've written PyAlf, which is an interface between Python and ALF, so a Python interface to ALF. And this is what we're going to use for this tutorial. What's the purpose of that? So first, the way we're going to be using it right now is exactly one of the reasons it exists. That means you can have a contact with ALF. It might be your first time with quantum Monte Carlo even, and that makes it easier. Second, it's a very important reason to have such an interface. You can, without much knowledge, and especially without having to learn anything specific about ALF or even Monte Carlo, you can obtain benchmark results. And even for those who use ALF more intensively or even change ALF, it can be a very convenient way. We ourselves, we use ALF, PyAlf, I mean, all the time. We use PyAlf to make some short runs, some test runs. So it's definitely convenient to have it. And today we're going to be using that. I'll share my screen now. Just a sec, and then you're going to be able to see. You're going to be able to see. I'm just going to share my whole desktop. I think it's easier like that. Then you should be seeing everything I see. So before I started here, I went into my shell, my console here in this case, and typed. Okay, you see lots of messages. I'm sorry for that. And typed something like, okay, I'm not gonna find here. So let me come out, and then I'm gonna see. I typed this Jupyter notebook. Let me make it bigger so that you guys can see. I typed that here, Jupyter notebook. So we went through the installation. Jupyter should be installed, and by running that, you are going to start the session, and it's usually going to open automatically on your browser. Some window like this one here. Let me also make it bigger. What you guys can see here is what in principle is essentially a file navigator, like Dolphin, like or Midnight controller, where you can see the files you have and like less modified time and things like that. But that does not matter to us right now. I can also go up here and take a look. So I am in PyAlf, in the PyAlf directory. So if you download PyAlf, and you can find just in the tutorial, if you download the PyAlf, and I mean we install that, you're gonna have all of those files and folders with you. You can go to scripts, and then you're gonna have you have scripts that you can run without the Jupyter, so it has nothing to do with Jupyter, just plain Python. But today we do want the notebooks, which for those who don't know, are essentially a very nice way of having high quality or formatted comments together with code that you can run and output of this code all in one place. We're going to start with the minimal ALF run. Okay, so you just click on it, and now it's being. Now, if you go back here, we're going to see that it's green, which means that it's running. So you can go to the running tab, and you're going to see that it's running. So you can go back here. So we start. Those are comments. This is also comments. And to go to run it, in the case of a comment, running means just applying the formatting or the links like here. You just press Shift and then Enter, and then it goes down. Okay, that's all you have to do. So every time you see it going down, I'm going to be pressing Shift and then Enter. I want to go line by line here, so that because this is really just about doing the very absolute minimum to get ALF running and producing some output and looking at this output. So the system we're going to be considering, of course, since you want to type as little as possible, is going to be the default system, which is the canonical Hubert model. And our default configuration is a 6x6 square grid. The temperature is a beta equal 5. The interaction strength is set to 4. All right. So first here, in PortOS, we just want to be able to interact with the operating system, so that I can tell you why, but we want Python to interact with the operating system. It's going to be clear why in a sec. And here's the part that is going to bring ALF into this notebook. So from a file, from a script called PyAlf, we are going to import something called the simulation. And with that command, we have the interface with ALF set. So I'm going to press Shift and Enter, and we'll go down. And now we come to the place where we're going to see in the later on in more complex examples, longer lists of parameters. Here once again, I want to do as little as possible, and I could actually, as little as possible actually would be no parameter set here whatsoever and use everything default. But that would be a bit too much. Then you really have no idea what's going on. So just for you to have an idea, I'm saying that the simulation is going to be at the Hubert type. Then I have a comma here, go to the next line and start the definition of how it's going to be done. The model is Hubert. That's the base model. The let's type is square. You have ladder, you have honeycomb. We're staying it square. And this is rather new. So if someone by any chance downloaded the PyAlf a few days ago, you don't have this. It's just so that we don't, in the installation, many people complained of us downloading ALF all over again when you try to run PyAlf. So this is an instruction that, together, of course, with a corresponding change in the PyAlf interface, looks if there is an ALF already set somewhere and uses this ALF that's already installed. Okay, so here we are setting our simulation. So and this is the part that needs the operating system. It's trying to get some environment variable, name it ALFdir, and using it in case it's set. So I can also run it, Shift Enter, and we can compile. And as it's written here, right, it's going to compile ALF, and if not found locally, it's going to download it first. In this case, it's going to find it here. We can go through the compiling phase. It doesn't take too long, so I'm doing that. For those who never used the Jupyter Notebook, you see that here you have an asterisk, which means that this is still running. The command in this cell here is running. Another way, sorry. Another way of knowing that something is running is looking at the tab icon up here, and it shows ascend time, ascend clock. While the compilation is going on, I can already continue to the next step, perhaps. Though the next step is also going to take some time. It's going to run. The Hubert. But given the default, okay, it's done. Given the default, let's start then. Okay, so we're here. Same run. once again, Shift and Enter. So it's running. It says it created a new directory called Hubert Square inside of the directory alpha data in the notebooks themselves. It didn't find it, so it's creating it's new, it's creating it, it's making it, and it's running the executable from ALF called Hubert in this case. We chose that in our simulation definition. It's already over. So just to make it clear what happened here, I'm sorry if I wasn't clear before. So I said that I described what we did here inside simulation, but I didn't say explicitly. We called this simulation, defined the way it's defined here, we called it sim. So with this, this is the definition of our simulation, and that is gonna include all the methods that we need. So in the third cell here, we said sim and dot compile. We did that, and then we did sim and run, and that made this simulation as defined here with these parameters run, and it created the directory and ran it. Now we're gonna do sim and analysis. So once again, Shift Enter, and perform the analysis. By default, sometimes you might want to prevent it from doing it, but by default, it tells you what is analyzing. It was extremely quick because, of course, that's just a demonstration run. It might take a bit longer, but of course, it's faster than the run itself. And we can use this output to let's see what kind of measurements are made. So we have the energy, we have the potential energy, we have the kinetic energy, and they are self-explanatory. So spin T is totally spin. For example, that's the density. All those variables with EQ in the end means that we are talking about some correlation, some equal time correlation being calculated, in this case, the density. And when you have tau, so here, for example, I have spin Z tau, we're talking about the time displaced correlation of the spin tau, of the variable here. We can then get those because the analysis has been made, some output files have been created, and then you can, okay, let's get those. We read into our, can be script, or in this case here, notebook, by using, again, a method from sim, and it's called getSim. So here in this case, I'm storing in obs the dictionary, as it's called as it's called here, of the observables. You see, not all of them are being read. That's something we can change later on. For the current purpose, it's enough to read part of them. And you can finally see what came out of the simulation. So what came out of the simulation? Of the observables, I'm gonna get something called energy scalar J, and get the observable from it, and the value is, it's not defined because I didn't run it before. So always run in order. So now I ran it and got and actually defined obs as being the output of, or the result of get observables from the same instance. And here we can then see which value was obtained. So we got something that's close to minus 30 with an uncertainty of 0.1 essentially. And then let's start that soon because it's going to take a bit of time, but let's be patient. We can, or I can interrupt it. Yeah, I guess I'm going to interrupt it. So I'm not going to run, there's no reason for running it. We can do the same thing again without all those comments and intermediate steps. So what I'm doing here is I'm going to run it again. I did that before, so we can look at the output and then tell what happened. So I'm getting the same simulation and running it again, the same simulation and analyzing it. And then I'm getting obs2, which is just a different name for storing my new results of the analysis. And then I get those observables. And I'm doing that why? Because I want to show the following. When I run and I'm not in a new folder, or I didn't delete the folder, the data folder, then it's going to be detected. Let's say, prepare the folder for Monte Carlo run, and says, oh, actually there is already one. And then it says resume in previous run. So that's a feature. Once it finds a directory, once you find yourself in the same directory and it has already data there, the analysis is going to use it's going to run as if it was a continuation run. It's going to use data there and it's going to be analyzed all together. So it's just something you have to be aware of. If you want it, it's good. If you don't want it, then you have to take care of to prevent it from happening. So you have to, for example, delete the folder or change its name or move it somewhere else, because otherwise it's going to be used. So in this case, it detected, and then it ran again. It performed the same analysis. And then why do you do that? So what do you get from running it again? Well, I have more data, and if you have more data, and we're doing a statistical analysis, in this case, we're doing, for example, simple averages, let's say, you're going to just obtain more precise results. So in this case, the minus 29,894 went to minus 29,84. So it changed a bit. It changed a tiny bit in the second slot after the comma, and the error, which had been in the first place after the comma, so 0.1, now is reduced, in this case, by half. I find it a bit surprising it's reduced so much, but well, that's how it came out here. So it's reduced by it's reduced to 0, so from 0.1 to about 0.05. Okay. And again, why did it happen? Because it resumed the previous run. Right. So you have better statistics. That's it. Okay, and that's the example of this first exercise called minimal ALF run, and that's what there's to it. You have your parameters. Of course, you can customize as many as you want, or if you don't want the defaults, you compile if you need. Often it has to be done only once, and then you run your simulation, analyze it, and then you take a look at your data. Right? You can run again if you want to improve the statistics. So as exercise, and again, don't start now. We are going to continue to the next example. And I'm way over time, actually. So if, I apologize for that. If, it would be very nice if you guys could take the time to rerun once again and check if there is some improvement, or if actually, and yeah, I can already tell you beforehand, so that's not so exciting anymore, perhaps, but you're not going to see much improvement, which probably means that the limitation in precision is somewhere else in the code, not in the amount of data obtained this way. But you should check for yourself, or you can check for yourself if you wish. Take a look at the other observables that are available, right? If you know the expected values, you can also check against them. That's always useful. And last, venture yourself into changing this part here of the code. You see how it goes, right? Try to, if you don't know Python yet, try to emulate how it's been done here. So if you're going to put a new variable here, remember the comma after that and the way the quotes are being used here. And I want you to not use the default 6x6 square grid, but I'm suggesting that you try a ladder, essentially a 4x1 grid. Okay, so that will be it with the minimal ALF run. Yes, I can leave. So let's come here. Went to the minimal run.
Jefferson?
Oh, yes, sorry.
There is a question in the chat by Hui Shao. Maybe you can answer that.
Let me take a look at the chat. How can we know how many beans have been generated and how many samples are there in one bean? You can take a look at the defaults value. So let me bring my console here. So I'm now, let me make it big again. So I'm now at notebooks alpha date. We don't need that. I am in PyAlf, and you can take a look at this file here. It's called very tellingly default variables. And then if you want to know something about, if you want to know, for example, how many beans have been used, then you can come down here. That's not a nice way. You can also output that, okay? But either way, you can look at this here. Number of beans, in this case, is only 5. So it's a very modest number of beans. Okay, and the number of sweeps is 100. I hope that answers the question. If not, just let us know. Just let us know. All right. So my next example would be then the Trotter error. I'm not going to go into the physics of it. There's no time for that, and it's anyway better covered in the documentation and has been already mentioned today by Fak in his talk. But you know that we have an error that goes with the square of delta tau, right? So let's go through the same spots, steps. We are importing the operating system, that's a detail. We're going to import from PyAlf the simulation, that's good. Here we have some extra stuff. We want some Python libraries so that we can plot and calculate extra things. If you want to do that through Python, you can. If you want to output your data and use some other language or platform, of course, you're free to. It's just convenient to do here since we are in a Python notebook, or in a notebook, a Jupyter notebook that uses Python. All right, so we just bring the simulation again. And what we have different here is that I want to see, so the purpose of this notebook is to show this dependence, just square dependence. And for that, I need different, since the dependencies in delta tau, I need different values of delta tau to confirm that indeed the error varies like that. So that's what I'm doing here. I'm creating, instead of my simulation being just the same equal simulation, like it's still yet here, I have a previous step where I'm going to create an array, actually, and I'm going to put those different simulations for different delta taus in this array of simulations, okay? So it's normal programming, actually. It's just done here in this, yeah, we don't have to declare that's how Python works. You just say that it's an array, it's gonna then take the type it needs to take to work. So going here, I'm defining this array, and then I just want to print here, that's being printed down here. Okay, the tau values used are such and such. And then I loop it for the tau varying according to this list here, 0.05, 1, and 2. I want you to, and then you see, I want you to sim equals simulation, so I'm creating different instances of this simulation. They're all Hubbard, they're all square, they stay 6 by 6, so this is unnecessary because those are anyway the default values. But I included them here so that you can see better what's going on. In particular, you can see that now we're going to use a larger number of beans, we're going to use 10 beans, and also a larger number of sweeps, 200, so that we get a bit better results. So you have all those values here. There are many more parameters, of course, but I'm showing some of them here. All right. So I'm creating this array of simulations, templates, simulation instances. Then if you need to compile, there's a small detail. I'm just compiling the first instance because, of course, compile three times after the other, 3 times in a row is useless, is unnecessary. So that's why there's this detail here, but it's just exactly the same as we did it before. And then you run. Of course, instead of just saying same run, now we're going to say that's loop over the instance that we created and run please each one of them. And that's clear. Also in the output from the notebook, it says, okay, I'm preparing the directory. I have to create it because it did not exist yet. And then I'm running the Hubert out. And it does that 3 times because we have 3 instances of the simulation because we wanted to have 3 different delta taus. That done. So once again, I'm not going to actually run in real time because there'll be a necessary waiting. Once that's done, then here there's a bit of detail just so that I can print the way I want. So I'm saving the energy values in a matrix, and and I'm preparing a vector, an array, as you wish, to store that's the delta tau, sorry. So here I'm preparing the energy vector to store the observable, and here I have the delta taus, which we already know. And for here, once again, I have to loop and I perform the analysis, being careful to store them. So the delta taus are just being stored here. That's okay. We know what they are, and here I'm storing the energy values. That runs quickly, and this step is not. So we want to say I'm showing the data in two different ways. First, I'm printing the energy, so that's what we obtain here, those three values here. And later on, I have here the commands, so you can or cannot take a look at how you can make this plot in Python. And I'm putting the same values as the same information, with the exception that I'm also doing a fitting here in the plot that you can see here. So what I'm plotting here is already squared so that I get a straight line and can see clearly that we do have a quadratic dependence. You see this straight line because I'm squaring already the delta tau. So just to just to make it clear, xs is defined in terms of the delta taus here, okay, and then I'm squaring them here. All right, so that's shown here. 0.04 is the square of 0.22 and so on. So it fits. Again, this is a quick simulation. That's why I have such big error bars. It all can be improved, but it's better for demonstration purposes to be like that. In the exercise we suggest you, in this case here, is to explore what happens when you vary those parameters here, the checkerboard and the symmetrization parameters. So if you use a checkerboard decomposition, and if you use a symmetrization. So we have either true or false for each of them. So you have 4 possibilities, 4 combinations. It's interesting to explore. You can check your results against alpha documentation in figure 2, section 232. We have the results for that already, and you can see what happens. Essentially, it's an example of how symmetrization actually can be very helpful. It improves the results considerably. Our next example is testing against ED. We have an exact value here we want to test against, minus 1.47. Again, the quadratic dependence is there. Our system is now finally different. It's not going to be the square 6x6 or 4x4. It's actually going to be a ring. So it's a one-dimensional lattice. And this first step, I guess, we've seen already twice. We don't need to go through it. The second step here, I'm just going to call your attention to the fact that we have a specific lattice type called any leg ladder. It's convenient. Of course, in principle, we could use the square lattice, but it's convenient to be like that. And then I'm making, it has 1 leg and it has only 4 sides. So it's a very small system that we're simulating here. The delta tau values we're using, you can see here. And then, as before, we compile one of the instances if you need. We loop over those different instances of the simulation, which means they all have the same parameter values except delta tau. So we run them 3 times. Once again, we prepare our Python variables to store the results and to allow them to be plotted in a nice way. And very similar to the example we just saw, we obtain, once again, of course, you can look at the values, remarkably precise. And if you look at the plot, it's also very nice. If you extrapolate from those 3 dots choose 0, to delta tau 0, you get a value here that's between 470 and 1, minus 1, 470 and 1475, which probably means 1725 or so. And I remind you that the expected value is 4726. So very well reproducing the expected results, even in a tiny lattice. Florian, what do you think I should go on with my last example, or are we too much over time?
Technically, we are behind our schedule. How long do you think will your last example take if you invest?
If I rush a bit like I've been rushing with the previous ones, let me take a look. We should finish. Yeah, we should give time for the. Yeah, no. I think the problem is that people might be waiting to listen to.
Exactly.
Yeah, exactly.
So if you,
I think we showed enough. I apologize for taking longer than I expected, people. Please do come back with questions and take a look at the tutorial. All of that is there, as well as the examples. Okay. Thank you very much for your attention.
Thank you, Jefferson, for that nice overview over the tutorials. Maybe you can do the last tutorial later on. So to all the participants,